Hello friends, welcome back to the online lecture series of fluid mechanics. Till now we have finished with the fluid properties and are on our next module, which is fluid statics or fluid at rest. Today we will be discussing a very important topic, which is the hydrostatic condition. Hydrostatic condition. Now we know that in a static homogeneous fluid, a fluid particle retains its identity for all the time, or a fluid particle do not deform. Now we know that fluid at rest is acted upon by two type of forces. First is the body force, which is of course the weight of the fluid under the action of gravity, and second is the normal component of the surface force, which is termed as pressure in case of fluids. So for fluids at rest, we have these two type of forces that are available to us. First is the body force, or the weight of the fluid under the action of gravity, and the second was the normal component of surface force, the normal component of surface force, which is termed as pressure in case of fluids. The normal component of surface force is available to us because the necessary condition for a fluid to be at rest is the absence of shear stress or the absence of angular deformation. So the only surface force that is remaining to us is the normal component of the surface force, and this is known as pressure in case of fluids. So we can say that the state of rest is governed by the equilibrium of these two forces, the body force and the force due to pressure. So at static equilibrium, we can say that the body force and the pressure shall be mutually interconvertible. So this is an important point to be noted, that the body force and pressure shall be mutually interconvertible for a fluid to be in equilibrium, for a fluid to be in equilibrium. Now, the hydrostatic condition. What do we mean by this hydrostatic condition? The hydrostatic condition simply involves the equilibrium of a fluid particle. So basically, we will talk about the equilibrium condition of a fluid particle. Equilibrium condition of a fluid particle. Now, before discussing the equilibrium condition of a fluid particle, let us try to see what do we mean by fluid particle, or how to define a fluid particle. This fluid particle may be defined as a body of fluid having finite mass and internal structure but negligible dimensions. Now, the fluid particle is very small, but it is large enough that the continuum hypothesis remains valid. So, a fluid particle have definite mass and internal structure, but negligible dimension. This fluid particle, or sometimes we also say the fluid element, it may be delineated or it can be identified through a boundary in a continuum. So when we talk about hydrostatic condition, the hydrostatic condition means that each fluid particle is in force equilibrium with the force due to pressure balancing with the weight of the fluid particle. So there will be a force equilibrium force equilibrium, in which the force due to pressure, balancing the weight of the fluid particle. Now this may be demonstrated. Suppose, let us say, let us assume that there is a fluid particle in a fluid at rest. So let us say that this is a fluid particle, and it is of course in a fluid which is at rest. So let us say that this is the container which is containing the fluid, and the fluid is static. Now the two type of forces that will be acting here, first will be the body force. So first we will draw the body force, which is actually the weight of the fluid. So this is FB, or the body force. Now this fluid particle will be under the action of pressure of the fluid. So we will draw pressure like this. The intensity of pressure may be represented by using these arrows. So this actually represents the intensity of pressure, or you can say that this is the pressure distribution that is acting upon the body, and this FB is the weight of the fluid particle. Now under equilibrium, these two type of forces will be balancing each other. So we can say that for this fluid particle, there will be a force balance such that will balance the weight, and second will be the force due to pressure. Now these two forces are mutually interconvertible in case of fluid at rest. Now we have already discussed about pressure or the intensity of pressure. Now let's talk about the intensity of pressure again. We have already discussed a bit about pressure. So let us say intensity of pressure. For this, let us say that we have a soccer ball that is filled with air. So this is a soccer ball or a football, and we have air which is filled in this soccer ball. Now the molecules of the air interact with the walls of the soccer ball, and it produces a pressure distribution. So the air molecules are interacting with the walls of the soccer ball, and it is creating a pressure distribution. Say it is a pressure distribution is created like this. Now this pressure distribution, what it will do, at each point on the walls, this pressure distribution creates a resultant force and acting normal to the wall, or you can say that it creates a resultant force that acts on an infinitesimal area. So at each point we have a resultant force that will be acting due to pressure. So let us say that this is an infinitesimally small element or a point on the wall of the football or the soccer ball, and this we can say that this is an infinitesimally small area, infinitesimal area. Let us say that this is del A. Now the pressure distribution tends to create a resultant force that will be acting normal to the infinitesimal area. So we have a force due to pressure, you can say the force due to pressure that will be acting perpendicularly to the point or to the infinitesimal area. So let us say that this is del Fn. Now we define the intensity of pressure as taking limit with del A tends to 0. We have del Fn upon del A, which in larger terms we can write down dFn upon dA. Now the reason that this pressure has been defined using a derivative, it is basically because we will see that the pressure varies from one point to another point. Now here in this case we can see that the pressure, it appears to be compressive in nature, or you can say that it appears to be a compressive force acting per unit area, and it gives an impression that it is a vector quantity. However, pressure is not a vector quantity, it is a scalar quantity, because it has magnitude but no specified direction. It does not have a specified direction. Rather, pressure at any point in a fluid is same in all the directions. This we will be seeing in our next topic of discussion, that the pressure does not have a specified direction. Rather, pressure acting at a point is equal in all direction, and this is a statement of a very important law which is known as Pascal's law. We will discuss about Pascal's law after discussing this. So this pressure is not a force. Pressure is not actually a force. It is a scalar that produces a resultant force by its action on an area. So we cannot say that pressure is a force. It is a scalar quantity that produces a resultant force that will be acting perpendicularly to the area upon which it acts. And the resultant force is normal to the area, and it acts in a direction towards the surface, or direction which is perpendicular to the surface. So pressure is not a vector quantity. Pressure is rather a scalar quantity. It has a specified magnitude but no specified direction. Pressure at a point is equal in all directions. So we cannot say pressure as a force. It is rather the pressure, what does it do? It produces a resultant force upon the area upon which it acts. That resultant force will be perpendicular to that area. So let us now discuss about Pascal's law. As we have already discussed that the pressure is a scalar quantity, and it has magnitude but no specific direction, because the pressure at a point is equal in all directions, and this comes from this very important law which is known as the Pascal's law. So Pascal's law, or Pascal's principle, or this is also known as the principle of transmission, the principle of transmission of fluid pressure. Now, as the name itself suggests, that this law was established by a French mathematician named Blaise Pascal. So it was established by Blaise Pascal. Blaise Pascal was a French mathematician. It was established in the year 1653. However, it was published after a decade, that is 1663. Now let me write down the statement of this Pascal's law. The Pascal's law states that a change in pressure at any point in an enclosed incompressible fluid at rest, it is transmitted equally and undiminished. And undiminished to all points throughout the fluid, to all points throughout the fluid, and the force due to pressure, and the force due to pressure acts at right angles to the enclosing walls. Now this is the statement of the Pascal's law. Let me again read it for you. That a change in pressure at any point in an enclosed incompressible fluid which is at rest, it is transmitted equally and undiminished to all points throughout the fluid, and the force due to pressure acts at right angles to the enclosing walls. What does this mean? This simply means that if there will be a change in pressure at one point in an enclosed incompressible fluid, then that change will be transmitted equally and undiminished. By undiminished, we means there will be no change in its intensity, or there will be no change in the magnitude of the change in pressure, and that the change is transmitted equally and undiminished to all the points throughout the fluid. If you take any point throughout the fluid, it will be the same everywhere, and that force due to pressure, it always acts at right angle to the enclosing walls. To the surface upon which that pressure will be acting, it will be acting normally to that surface. Now this statement can be also written in a very simpler terms. You can say that pressure at a point, you can say that the pressure at a point in a fluid at rest is equal in all directions. Or if we draw, suppose this is a point upon which the pressure will be acting. So a pressure at a point in a fluid at rest is equal in all directions. So it is acting upon any point, the pressure will be equal. Means if you take the magnitude, it will always be same at that given point. And through this definition, we see that if there will be a change in pressure at one point, then throughout the fluid, the same change will be occurring, or we will feel the same change at any other point throughout the fluid. And the force, there will be a force due to pressure. That force will always be acting at a direction perpendicular to the surface. This is what we mean by the Pascal's law. To make things more clear, let us see one example. Suppose we have a glass tube, a U-shaped glass tube that is filled with certain fluid. Suppose we insert two plugs on both the ends of this U-tube. Let us say that these are the two plugs, or rather we say that these are the two pistons that will be acting on the two limbs of this U-tube. Now if a pressure P1 is acting on the left piston, then the pressure will be transmitted throughout the fluid and it will be felt by the right piston. So we have a pressure that will be acting on the right piston. Let us say that it is P2. So the pressure that will be acting on the left hand side or the left piston, it will be transmitted throughout the fluid, until it reaches to the next piston, which is the right piston, and the pressure that is acting on the right piston is said to be P2. So according to the Pascal's law, we have P1 is equal to P2. So the pressure is felt equally at any other point. Let us say that the force due to this pressure P1, it is F1, and the area is A1. So we have F1 upon A1 is equal to F2 upon A2. Now from this we can calculate F2 as F2 will be equal to A2 upon A1 into F1. Now this A2 upon A1 is also named as the mechanical advantage. Now see, if both the pressures are equal, if the pressure is equal, P1 is equal to P2, we have F1 upon A1 is equal to F2 upon A2. From this we get F2 is A2 upon A1 into F1. Now if we take both the areas, if A1 is equal to A2, then from this we will get that F2 will be equal to F1. Also, if we make A2 50 times more wider than A1, then what we will get? We will get F2 will be equal to A2, which is 50. A2 upon A1 is 50, so we will get 50 F1. So if we apply a force of, say, if F1 is equal to 1 Newton, then on the right hand side we are going to get F2 is equal to 50 Newton. This is a very important application of the Pascal's law, and this is used in many devices. So here we can see that we are actually, what we are doing, we are multiplying the force, or it is acting as a force multiplier. Even though we are applying a very say very less amount of force on the left hand side, we are able to get a force which is 50 times the initial force in this condition, and so this can be used as a force multiplier. And this is actually used as a force multiplier in many applications. Thus we can say that the forces can be multiplied using such a device. And this Pascal's principles, the principle which we talked about, the Pascal's principle, this is used in operation of many devices such as the hydraulic press, or even in case of hydraulic jack, which is used in automobile service stations. There are many more examples in which this principle has been used or is being used, which includes the hydraulic braking systems or the hydraulic pumps. Even in case of civil engineering, in case of dams and reservoirs, we have the hydraulic lifts, valves and spillways that acts on this principle. Even we have hydraulic lifts and elevators that uses this principle. Or if you see the aircraft landing gears, they are also using the same principle. In fact, there are many more applications of this Pascal's law, and it is the most widely used principle that we use in our daily lives, be it in automobiles or in civil engineering, or even in our the elevators and lifts that we are using in our everyday life.